So today we've got Dylan Richard with us. We've got Anthony. We've got Brian Wilson and Chris Clater from the Beck Group. And we've got Bill sitting over there.
Yep.
That's an old picture of Bill, but that's all right.
We actually got a Jim, and then Richard's going to fill in.
Oh, I'm sorry. Anthony, all right. Sorry. We don't have Anthony. Anthony's out.
We don't have
missing Bill.
We're missing Bill. All right. I'm sorry.
That's an old picture of me.
It's all the formal pictures. I can't tell who's here. Sorry about that. Anyway, we've got structural engineers here, and that's the important thing. And we're blessed to have Richard Temple too. So Richard kind of drives the show over in Tampa, and I'm just going to turn it right over. So in addition to these sessions, we do have two in-person tours that we're doing. So we're doing this actually this semester, next semester, and the following semester. We're doing 2 tours on site twice a week. And we'll do those in, I think it's early February and mid-April next semester. Then we've got 4 online sessions next semester. We're going to be talking about totally different topics. We also have technology called either Constructionscape or Open Space, where you can actually, it's kind of like a Google Earth for construction, where you can walk around the construction sites, actually jump from circle to circle, do a 360-degree view at those particular circles, and then jump back a week, jump back another week, jump back another week, so you can actually watch the construction going on from a particular location. I think that is pretty cool. So you can get that either if you just Google USF AEC Connect, and we do post both these recordings as well as the PDF presentations online on the campus site. So I'm going to turn it over to Dylan and let you talk about general ideas of the different structural systems.
All right. And did you happen to see how many do we have online? I saw one.
There's at least 3 or 4 online.
Oh, excellent. Good. All right. And then we have 1 student in the room. So welcome.
One student in the room, a bunch of engineers in the room, and I do know that when we post this on YouTube, it does get additional views too. So
okay. Outstanding. All right. Well, thanks, Steve, for the setup. Online, can you hear us just fine?
Yes.
Great, thank you. All right, so start with just a general overview of structural systems and kind of the different structural systems that are out there. And then we're going to go from there and actually talk about 3 specific buildings on campus that Steve mentioned, and talk about the different systems that were used for each and a little bit of why. You know, every building really based on its layout and the market and the contractor that we have building it kind of has different needs. And so that's why when you go around and see jobs under construction, you see all kinds of different materials out there. So we'll just start kind of from the basics. You know, what is a structural system? You know, this is obviously a very old structural system, but one that's standing the test of time nonetheless. So in its simplest forms, your structural system starts at the foundation, right? You're at the ground, and this is what your building is going to actually sit on and transfer the weight and the loads of the building down into the ground. And then on top of that, we would have vertical elements, which we are calling columns. And the columns are what take the load from the floors. So floors can be framed out in many different ways. Right here is an example where we have a series of beams. In this case, these would be steel beams, but they could be concrete beams. So these are intended to have the load that your tables, your desks, the people that are in the room, it takes all that weight and gets it out to the columns down to the foundation. But to just have a building up like this, there are ways you can connect the beams to the columns to keep the columns from wanting to just topple over. But oftentimes what we use is bracing. So here I've turned on just some what we call X-bracing for obvious reasons. We call it that. But sometimes we actually, in the place of those, even have walls, and those can be done out of concrete. But what those are intended to do is to keep the structure from wanting to just topple over, or when wind is blown on the building, or if you're out west, you have seismic that wants to shake the building. This is what takes the load from the floor levels down to the ground. And then we tie all these together with the floor system. Oftentimes you end up with a concrete floor, but it could be wood, it could be made of several materials, but this is the actual working surface, whether it be where a person walks on, or it be the roof on top of the building where your envelope is. So the selection of a structural system, as we said earlier, many things can go into that. A lot of times it's time and schedule. Sometimes it could be, what's required for this building to perform its intended use. The site conditions, the daily economy can change. And from one year to another, a building might be better for steel and might be good for concrete the next time. But where we always start is, what's the use? You can see here we've got a courtroom, which has a few people in it spaced out. On the upper right, that's a roof. So there's not going to be a lot of load other than the mechanical equipment. Lower right, you see a library. Libraries are actually, although they're quiet and not real active, they actually require quite a bit of load because the books are pretty heavy. And then, we have our Yuengling Center. I still call it the Sun Dome, but the Yuengling Center. So, that is going to stack thousands of people in it at one time, jumping around and having a good time. So we first got to understand what the use of the building is and how it's going to be loaded. Then we want to take a close look at the economic considerations. So, what are materials costing? Right now, we're in a time period where material prices are really going up high, and they've escalated. So on new projects today, material cost is very critical, because it could actually make or break a project. What labor is available out in the workforce, and what equipment is needed. How quickly is the building needed for the owner? One of the buildings we're going to talk about is the new indoor practice facility for the football team. It's needed very quickly because we got a great new coach here, and he's looking to build and do new things, and it's critical for our recruiting, to have that building put online as quickly as possible. So schedule is really important. And then maintenance costs. We have to not only look at the building for building it from the beginning, but also how well is this building going to be maintained, and what's it going to cost to maintain it over its life. So those are some market conditions. The economy weighs into it. What materials can we get? How long does it take to get the materials? These all weigh in. With the schedule, sometimes we look through different systems, and a couple that are pretty common are concrete and steel. Precast is a form of concrete. That's just concrete that's cast off-site and then brought to the site in pieces. But a concrete job, like what the USF Honors Project is, they can get out and form and start to pour that pretty quickly. But steel has a lot of prep the work that has to be done in a shop. So concrete can get going real quick. Steel takes a little longer, but it actually can be erected very quick. So those are things that have to be weighed into when we talk about schedule for buildings. And then we do have to look at what future modifications is this building going to need. Are we going to have to cut new openings in it at some point in the future? Are we going to have to expand the building? Is the type of usage, the occupancy, going to change at some point? So these are all things that are good to know up front as we select a structural system. So the common systems are steel, cast in place concrete, precast concrete, masonry units, concrete masonry units, also known as CMU, and then wood. So just real quick, give you just an image of some of these, and this should start to be able to stand out for something maybe you've driven by on job sites and seen before. So this would be an example of a steel building. Here we have an example of a cast-in-place building where you see a lot of posts and shores and forming, and then the concrete gets cast onto it. Here's an example of precast. Precast you see a lot in parking garages. This is where you'll see they'll actually bring out large pieces of concrete on trucks, sometimes 50, 60, 70 feet long, and they will essentially assemble them in the field. So it's kind of like when you played with Tinker Toys growing up and you build all the pieces together. That's how a precast job is put together. They're cast off site and then they come together and are connected in the field. And then masonry. Masonry is an interesting product because it's actually built in units that are 16 inches by 8 inches by 8 inches. They weigh about 45 pounds a piece, and they take and they can put those together with grout, and then they fill the walls with concrete and reinforcing, and then you can add steel framing into them. So this is an example of a masonry project going up. And then there is wood, by far the most sustainable of all the products. And wood you see a lot in residential, but it's starting to make a pretty big comeback in commercial as sustainability is becoming more real, and our emphasis on the carbon footprint it becomes more critical. All right. And with that, I'm going to turn it over, and Jim Maraday is going to go ahead and talk about one of our projects right here on campus that is soon to start construction that you'll be able to watch go up.
That's right. Thank you, Dylan. I'm going to talk about the indoor performance facility. It's a project that I was design engineer manager for. I believe some site work has started and foundations will be starting soon. Next month or so, Steve, maybe?
Fence goes up on Friday after Thanksgiving or Monday after Thanksgiving.
All right, Monday after Thanksgiving. So the performance facility here it's over off of Sycamore Drive, and I think it's going to serve a great need on campus. It's Florida climate is one thing to be performing or be practicing outside all the time. So we're going to put in a new indoor facility over at one of the current outdoor practice facilities. And this structure, it's a unique structure that sort of falls under the steel umbrella, but it is a pre-manufactured, pre-engineered metal building structure. So on the left, you can kind of see the main structure that covers, think about the size of the football field and the type of structure that would be required to enclose that. And then on the right, we have kind of an auxiliary structure that is tied into the main metal building. That's kind of a lobby entrance area. So here is an isometric of our structural model, and we produce this in a program called Revit. And this is kind of where we house all of our structural information. It's where we produce our structural design documents that get submitted for permit. And we, as the engineer of record, have defined everything that this pre-engineered metal building. We've defined design criteria. We've defined kind of all of the dimensions, elevations, grid dimensions, size, spacing, all that type of stuff. And then a pre-engineered metal building supplier will delegate all that information to them, and then they will provide the design for that for the building. And the reason that it kind of works that way is that these guys kind of have a turnkey system that's very efficient. They design, they engineer, they fabricate, they erect this building. And so Dylan mentioned schedule is always a big component for this type of project, and this type of large facility can be produced pretty efficiently by these pre-engineered suppliers. If you think about the function of the structure, there's not a lot of building types that could span over a football field, both width and length. A lot of times you'd need to drop in columns, that type of thing that is not conducive to what's going on inside this building, right? You've got football practice, you've got people kicking field goals, that kind of drives the shape of the structure. So the system itself is really driven I don't really have a laser here, but you can see that every 20 feet or so, there's a sort of an arch frame that is made up of steel members that are sized, by the engineer. And each one of these is what we call a lateral moment frame. So it can resist wind load in and out of the building here. And one of the unique components about this type of structure, if I touch briefly on foundations, is you can kind of see between each one of these frames underground is what we call a tension tie grade beam. And the reason for those is if you think about all the load pushing down on these frames, there's going to be a huge thrust force. And so we need some way to resist that. And so we've essentially tied these together with grade beams that are mechanically spliced together with a lot of rebar, essentially, to resist that large tension force. Some other components, along these end bays, we've got a lot of columns that distribute, the wind loads to the frames. And then, as I mentioned before, this auxiliary structure here in the corner, that's more of a traditional structure. That's steel columns, beams, metal deck. And then we also have a lot of X bracing that Dylan mentioned as well to kind of resist the lateral loads long ways of the building. So here's an elevation straight from our drawings that shows one of these lateral moment frames. And as I mentioned, we define kind of all the parameters that are the metal building supplier then adheres their design to. So we've provided kind of the height of the structure, which is 65 feet there, 68 feet there at the peak, driven by the function of a field goal, essentially. We've given column size, heights, dimensions that we've coordinated with not only the architect but the owner and the MEP engineer. Going here's another elevation now of the long ways, kind of showing how we're defining bays in which we have lateral frames. Again, in this case, we're using X bracing. Again, coordinated to the function of the building. We've avoided bays where there's going to be doors or canopies or that type of thing. So here, now we've submitted our drawings as engineer of records, gone out for permit. The contractor, in this case, R. Simmons, has secured a metal building supplier, and we've received their design, which is what we see here. This is pretty hot off the press from the shop drawings that we've received. And you'll notice not only are all the main structural frames there that we specified, but also kind of all the infill framing. So how does the load actually get to all of those main frames? There's a lot of purlins on the roof that carry all the roof panels out to those main frames, and then along all the walls we have what they call Z-girts, essentially a thin plate beam member that looks like a Z that kind of frames and supports all the cladding and distributes the wind loads to all of our frames. So unfortunately, this structure is not under construction yet, but we do have right here in Tampa one Buc Place, which was 2017. Happens to be the same metal building contractor. Canco was on this structure as well, and we were the engineer of record on that. So I have some photos to kind of show the construction of that structure. I don't know if you've been out there to see that, but it's a pretty cool building. So on the left here is kind of the initial erection of those big columns. The shapes here are a little bit different than what we have on this building, but again, it's all driven by the use of the space and what kind of cladding system this particular building had.
It's the shape. It's the same contractor and the same shape. Why would the structural members be a little bit different?
It's the same contractor, but it wasn't. They used a different engineer for that. And then there's also a lot of different cladding on this one. They have a lot of glass down low around
this one. The Bucs was 95 feet tall.
Okay.
And had a little bit wider footprint.
The actual metal building manufacturer is a different manufacturer.
That's right. So here is the same building, a little bit further along now. All those, you can see all the frames down the length of the building have been erected, and they're starting to do all kind of the infill members, the roof purlins, the Z-girts here on the right-hand side. And a little bit further along still, they're now starting to clad the building. So they've got the, I forget what the roofing system was on this, if it was just metal panels or different type of roofing system, but
Insulated metal panels.
insulated panels.
That's right.
And then they'll start to enclose the walls and the sides and glass and all that kind of stuff. And finally, the finished product. You can see here how they integrated kind of the glass that looks out onto the outdoor playing field. Kind of the lighting and some of the things that hang from the structure that add to the loading. And that is what I have. So Bill McNally was going to present the Student Wellness Center, but he's not available today. So I think Richard Temple is going
I'll try to wing it.
to jump in here for us.
Which
Richard?
is where we,
Down here.
this?
Yep.
Okay, standing in for Bill McNally. Bill McNally has been with Walter P. Moore and Associates, 10, 12, 5, it's more than 5. But anyway, outstanding engineer, but he deserves time off, and so he's not here today, so I'm standing in for him. I've been with Walter P. Moore for far too long, so. We've done a lot of projects at the University of South Florida. The student wellness is one that was gone. It was a design build process, right? The selection, and it's a pretty competitive process by which each of the contractors gather their team together of architects and engineers and then submit their qualifications. And as the qualifications are then reviewed by the university staff and facilities, a selection, a short list is developed, and then those firms are then interviewed, and the best qualified is selected, and then there's a negotiation process, and off we go with contracts, and then we get into the design and the details of it. So that's basically the process that we went through on the or the University of South Florida Student Wellness Center. There's other procedures that are used. So once the overall team has been selected with the architect, we work closely with Canon Design in this particular case, and developed through a series of iterations the different types of structural systems that could potentially be used. How many levels? Was there a one-story section? Where the elevators are? You can see these tall sort of concrete sections, which is where the elevators and the stairs are. There's a bit of negotiation back and forth as to do we want cast in place concrete for those, or masonry, or what's the appropriate system? Why not just use diagonal steel? We've gone back and forth on this particular system, but this is what's called the lateral load resisting system. We typically try to put that at the stairs and the elevators. It's sort of out of the way. We have found concrete, cast in place concrete is often the quickest, going back to Dylan's comment about schedule, is often the fastest way to go. May have a little bit more volume of material and that sort of thing, but it also tends to be thin and out of the way. So that's typically what we have tried to do. For the floor framing system, on some projects, we actually use concrete, or we will use precast. In this particular precast panels, in this particular project, we looked at steel, and we looked at different spacings and sort of refinements of what the steel structure would be about. So this is the overall system, the gravity system that you're seeing in green, the beams, and then the lateral load system. So very quickly, Dylan already touched on sort of load path. As a structural engineer, we got to figure out where the floor loads go, where the wind loads go, and how do they get down to the ground. So progressively, we look at the composite metal deck, which spans between the beams. Then we look at the actual individual beams. Then we look at the girders that support those, then the columns, and onto the foundations. And so we have some pretty sophisticated computer programs now that will analyze a wide variety of options to try to optimize what the right system, once you've selected steel, what the best system would be. There's also a lot of strict not guidelines, but standards associated with Steel Deck Institute standards, what the deck should be, what the gauge should be. So we compare that and determine what's the most effective and cost-effective system to meet the criteria for deflections, vibration, various other kind of requirements. So very detailed drawing here. Steel is great in tension, and concrete doesn't work in tension unless you put reinforcing steel in, so it's great in compression. So composite floor framing basically ties the two together. Concrete in compression tied with these headed studs, as they're called, the vertical elements, to the steel will make for a very efficient and actually shallow and very stiff floor framing system. So this is a very effective system once you've decided to go to steel. Going back to the programs that we use, there's various computer programs. We as a company have sort of focused in on computers and structures as the basis. That's a company as the basis of the program of, the series of programs that we use, the family of programs that we use to analyze buildings. This particular one, we use both SAP and ETABS for different components, and they tie together, talk to each other. We use our own individual spreadsheets and hand calculations too to check. You should always check exactly what a computer is telling you in terms of the output, because there can be some strange results sometimes. So it's always best to do hand calculations. Wind load on the exterior, obviously hurricanes, very simplistically here. Whatever the exterior wall system is, whether it's brick, glass, metal studs, obviously has to get transferred into the floors, and then through the floors, through a diaphragm design, as we call it, into the concrete shear walls, which basically provides the overall stability of the building. So that's the load path that we go through as an analysis. That's a critical component to start the design of a building, working closely, of course, with the architects. And we like color coded. Red is not good. Red is high stress, and yellow is okay and it's good. Green is really the best. So nothing unusual there, right? With traditional traffic light coloring system. So anyway, that's it. That's the wellness building. So now USF honors Mr. Anthony DeFurio.
Hi, I'm Anthony DeFurio. I am the structural project engineer for Honors College. I kind of jumped in on the project maybe about halfway through. There had been about a year of design, kind of the process that Dylan was talking about with looking at different systems, different materials and all that kind of stuff. So when I got started, most of that had been settled and we just kind of needed to figure out how we were going to make everything work. And kind of walking you through the sort of the overall process of actually building a building. Usually you start off with the architect drawing a pretty picture that everybody really likes and looks incredible and wants to be in. And that's kind of where we get started. We take a look at these pictures and start trying to figure out where we can fit structure and where structure is needed. And we go through and we use a computer program. Typically, we're using something called Revit that will build this whole model. And it'll basically build the whole building for you to look at and put everything just so where you need it. And we use that to kind of tell the contractor, what you need to build, what pieces you're going to need. Once that structural model is completed and the drawings are made and we know how much reinforcement needs to be in the slab and what size the steel beams need to be, we create a fabrication model. And people will go through and read our drawings and model pretty much every single stick of rebar. In the case of a concrete building like the one you see here, that's going to be needed for the supplier to actually manufacture in the factory and ship out to the site. So to start with, your buildings, when you're building your building, you start on the ground, and these are the foundations of the Honors College building. There's a lot of back and forth about this. The site is very not good. I think the geotechnical engineer who took a look at the site said that it was the worst site he has ever seen in 30 years. That sound about right?
And that's saying a lot for Jamie.
Yeah, he's done a lot of work. And so eventually it was settled on doing drilled piers. It's kind of a little side note. when we were trying to give estimates to the contractor for how much concrete to expect, we were told to tack on a 2-time multiplier for the volume of the pier, basically saying if we say we need a 2-foot wide pier that's 50 feet long, we should plan on actually placing enough concrete to make a 2-foot wide pier that is 150 feet long, just because the concrete was going to seep out into the ground below. So yeah, what's in the ground is drilled piers. That's all these tall circles you see. In some places where we have generally our big lateral elements that other people have talked about, those big shear walls, we tie the pier groups together so that they can function together and perform a little better. And then for smaller things, there's a couple of canopies on either side of the building. There's a big monumental stair in the front. We do spread footings, which just kind of sit there on top of the soil. They don't have a lot of load, so they don't need to try to get down to limestone or anything like that. All of the foundations in this project are made of reinforced concrete, which is pretty typical. Sometimes you'll do steel pipe piles. I've done that before. Very rarely, you could do wood, but usually on a project this size, it's just concrete footings. Another little interesting thing about this, in an effort to reduce the amount of, reduce the carbon footprint of the building, we specified the strength of the pier at 56 days. Usually we'll say we need it at 28 days. But for this, we specified it at 56 days with the idea being that they can use less cement, which really drives the footprint of a concrete building. They can use less cement and give it more time to cure and sort of make the building a little more environmentally friendly in that way. And then we come up to the gravity system. This building is a little bit different from the other two you've seen in that pretty much everything is concrete. The beams or the columns are concrete, the walls are concrete, the beams between the columns are concrete, and the slab doesn't have a metal plate or anything like that. It's just concrete. This was done in part because you can see that the building has a kind of a swooping appearance, and it can be hard or very finicky to do with steel. Whereas with concrete, it's a fluid. So long as your formwork has a nice curve to it, the concrete will too. And so this allows you to kind of have those nice curves you see in the building up here at the roof. Moving on, here is isolated from that structural model we saw earlier. This is our lateral system. They're all concrete shear walls. They're all made of reinforced concrete. We like them because we can put them around elevators and stairs, and they'll stay out of the way of the architect. If we were to do something like a braced frame, we'd have to find a wall we could put it in. Maybe have to wrestle with doors or something like that. But with a shear wall, there's always going to be a wall there. It's required by code actually as a part of the fire safety of the building. So this was a project where these shear walls really helped well. And then this building has a very intricate facade for that work, where in some cases you can see in the bottom left here, a lot of that steel is exposed, or in the bottom here where it kind of comes way out of the building and is also exposed. You can go to something like steel because it's going to have a much smaller profile. It's going to be a little bit easier to erect. The concrete that we showed all requires a formwork to be built. Basically, you have to build a building under your building to make your building. But with steel, that's not the case. It holds its own shape. It's very strong, so you can just pick it up and put it into place. So for these big swooping shapes that project far out from the building, where we didn't want a big bulky structure, we added steel, and these are all the steel elements in the building supporting the facade. So here are a couple of pictures of the building being erected. It's actually right next door to Cooper Hall here. And we topped out this week, I think. They poured the roof of the 7th story.
Today.
Oh, is that today? All right. So yeah, here in the picture on the left, you can see this is the reinforcement for those piers. As you can imagine, they're very long, so they get poured, tied together. And then the hole is excavated. In this case, we used auger or casing, drove casing down into the ground, remove the soil, and then set the cages in. Once your foundations are in, then you start pouring framing up your columns and your floor slabs. The picture here on the left is a beam column joint. So sort of the top middle, that's your column reinforcement coming down. And then going from the bottom left to the top right, and here on the bottom right, that's all beam reinforcement. And then kind of everywhere else throughout, you can see the slab reinforcement. And there is there's a bit of a hierarchy when you just kind of look at this. The slab reinforcement is usually going to be smaller bars because it's only supporting the slab and the load that's on it. The beams will be a little bit bigger because they're supporting, multiple slabs framing into them, and then the columns might have, even bigger beams or bars, sorry, because they're supporting a couple of beams. Here on the left, there's a kind of a little bit better picture of the slab reinforcement, very uniform, and then a beam there on the right side. And also the formwork. When concrete is brought out for cast-in-place building, it's just a liquid. So you have to have formwork to hold it while it cures and becomes hard. And then here in the bottom center is the formwork that was needed for this job. Concrete gets stronger gradually over time. And so there is a period where the contractor needs to keep moving and keep pouring, but the building hasn't achieved its full strength yet. And so in those cases, you'll place shoring, which are all these little columns you see here, that transfers the load temporarily down to other parts of the building that have achieved their full strength. And here's kind of a finished product. On the west side of the building, there's going to be this big curved wall. That's kind of what you get once your rebar is in and your concrete has been placed and it's cured and you strip your formwork. That's what it looks like. And here's a picture of the facade support that's going in. This is saved for last, structurally speaking. That's all getting put in place, and that'll be holding up some glass and other facade, excuse me. And so that is the USF Honors Building. So now I'll turn it over to Brian and Chris.
Some more questions?
Sorry.
No, you're okay.
Ahead of schedule.
We're a minute ahead of schedule?
1 minute.
I'm gonna take my. Guys are in for a treat.
Yeah.
We got this, Chris. Got this. You all get to witness my professorial debut, so birth of a legend. My name is Chris Clater. I'm the Senior Project Manager for Beck, in charge of the USF Honors College project. I'll be taking this section for my boss, Brian Wilson, so hopefully he gives me a good bonus this year. All right, quick question for you. Get to be the sole person in the room. Discussions regarding project design and budget should include which of the following stakeholders? Owner, client, design team, construction team, or all the above?
I'd say probably all of the above.
Man, right on track. Was a tough one, but yeah, for sure. All the above. So we've heard Walter B. Moore talk a lot about the decisions that have to be made to get to a certain point, right? What type of structure do we need? And even if we can hone in on what type of structure, what does that actually mean?
They actually launched the.
Oh, polls.
Nobody heard the answer.
Find out who was listening. If anybody gets this wrong,
Hey.
100%.
All right.
I'll take it.
Everyone's paying attention.
Everybody's listening. I love it.
All right.
I was just one person in that.
There we go.
Sweet.
All right.
Okay. Thank you, Mr. Lafferty. So we definitely wanted to take just a minute and chat through how decisions are made sometimes. So why is collaboration critical? I'm sure you guys will all have a simultaneous eye roll with this next slide. Knowledge is power. It is almost as annoying of a saying as teamwork makes the dream work. Doesn't make it any less true. Knowledge is definitely power. So the more knowledge, the more information, the more different perspectives you can bring to a decision-making process, the more informed that decision is going to be. So all information is important. No matter how big, how small, it can and should in some contexts be taken into consideration. So this is just a quick list. By no means is it comprehensive, and it does jump across lines, so to speak. So a lot of times from the owner's perspective, project goals, metrics for success, hypercritical, right? What is important to the client, right? That should be a key driving force behind any decisions. From the design team, design intent, performance requirements, how does this structure have to perform, in what capacity, what's it designed for? And certainly aesthetic requirements. How does this thing need to look? And from the construction team, cost analysis, market trends, costing, schedule, the typical stuff you think of when you think of construction projects, right? How are we going to build it and how quickly are we going to build it? The beautiful thing about this is the design team can speak to construction components. Construction team has input on design components. The owner gets to talk about all of it, right? They're the owner. So how do we collaborate? How do we make these decisions? Some tools, techniques, traditional workshops, and charrettes. This is what you see on movies and television when somebody is sitting around a table and they throw a bunch of pretty pictures up on the board, or it's sitting around a table or a space, throwing opinions, ideas, and perspectives out there, right? Trend reports analysis. This is where we get into the meat of stuff, actual metrics, actual data that we can throw out there and use for consideration, and then comparison, right? Lean tools and processes. So lean is effectively a set of protocols and processes that have been established. Particularly relevant for us are the construction processes that have been established. They range across the board from schedule production management to decision-making analysis and so on. So the lean process that we typically use it's called an A3. It's a way to level out decision-making guidelines, right, or factors. So we, Beck, a lot of times will take this basic A3 template and add a whole bunch of stuff onto it to the point where it's no longer, we call it an A4 just because it takes it to the next level. We take into account as much information as we can. What we have up on the screen right now is a really good example of just a quick analysis or comparison. Back to what Anthony was just talking about for the foundations for the Honors College project, there were a handful of different foundation types that we could have looked at. Certainly, this one on the far left is your standard drilled piers. In the center is drilled piers with consideration for grouting, given the anomalies that we knew existed underneath the site. And then on the far right is a mat foundation. So just at a brief glance, these are the different scopes of work or considerations we took into account. Almost all of these are cost-based. So this was very much a cost-based analysis. What is the most economical way to achieve the required foundation? And this is effectively what it broke out to. So in the case of Honors College, like Anthony said, we moved forward with a drilled pier foundation and ultimately did have to take into consideration grouting to fill some of these voids that were in these key critical areas throughout the site. So basis of this entire class, structures, right? Back when we first started looking at this job, we started looking at what are our different options for our superstructure. Like Walter B. Moore said, we could go in a handful of different directions. Most obviously would be the cast in place concrete or a steel structure consideration, right? This is effectively an A4 that was done to compare the two options and really give some context to what these impacts would be and what these decision factors are, and actually weigh them. So we assigned a certain number or score for each one of these categories and saw how it shook out. Just to run through them, cost, obviously we got to make sure we take cost into consideration, not the only consideration, but something that very much needs to be at the forefront of everybody's mind, especially in this climate. So approximate cost during construction, GC costs, so on. Schedule. How quickly can we get this thing built, right? Again, just to hit on recurring themes, schedule is absolutely a consideration for the university. We have to take into account when this building needed to be up and look at the overall project schedule and how that impacted how it is we were going to be able to get this building completed. Design, certainly want to make sure we're collaborating with the design team, taking into account design components, requirements, so on and so forth. You can see here, aesthetic quality, right? Not only does this thing need to be functional, it has to accommodate the aesthetics of the building, both from a superstructure standpoint and how are we going to accommodate the facade. Permitting, pretty straightforward. Fire resistance, similarly, not much to touch on, but you can start to see how some of these different factors could get lost if you don't stay organized with how you're taking into account the different options. Other client considerations. This is definitely something we wanted to focus on and really wanted to bring life for the class here. So a lot of times people think construction and it's time, money, people, right? That's effectively what we as construction managers manage, right? That's our entire job. We manage risk, which boils down to those three items. So our impact as stewards of USF goes a lot deeper than that. So you can see here, flexibility for future changes. How flexible is this building going to be? Are we going to allow USF the ability to use this space both now and in the future, depending on what their needs are going to be, right? Minority engagement. This was huge for us. And you can see here in the ratings for our concrete superstructure, on the left is a concrete evaluation, on the right is steel. For concrete, you could see we had a huge opportunity to engage our local minority community and really make an impact, provide those opportunities for people who otherwise, or companies who otherwise wouldn't have gotten an opportunity to work on a job like this. With the steel, we saw it was incredibly limited. So we didn't want to miss that opportunity to at least take that into account in the decision-making process, right? Campus impact during construction. How disruptive are we going to be? Does either option cause more of a disruption than the other? ODP opportunities, that stands for owner direct purchase. So as a state agency, there is a tax credit that is given on any materials purchased. So we didn't want to miss out on any project savings because we were being blind to what opportunities may exist or present themselves as a function of the materials that have to be purchased in either one option. And then certainly, as Anthony mentioned earlier, sustainability, right? We're good stewards of USF and we're good stewards of our environment. How impactful are we being to the environment either way? Or how sustainable is this building? So you can start to see, once you start assigning these values to each option, how one option can really start to present itself as more favorable collectively. Other construction considerations, this is where we get to be a little selfish about things. Crane road requirements, how can we access the building? What is logistically, how do we get this thing built? And does any one option present more challenges than the other? Bracing and shoring, lay down areas. This is really the bricks and sticks side of things and what you would think of as traditional construction considerations. And at the end of the day, 76 won. It was a clear choice as far as what this superstructure needed to be, what this building needed to be built out of. So if we wouldn't have taken the time to really put some metrics to it, start defining what these different options are, it had really been nothing more than throwing something at the wall and hoping that it stuck and basing things on just sheer opinion as opposed to actual metrics and decision making. Really needs to be noted that this was done not in a silo with Beck, but in conjunction with the entire project team, design team, USF, and Beck, all looking at these different options and these different criteria and assigning the appropriate values and then coming out on the other side aligned on what the decision is. It helps provide ownership for that decision. That way everybody comes out the other side feeling like they had a hand and we're all aligned pushing forward. It makes for a much better decision-making process and frankly makes for a much better project. That's it.
Feel like I killed it.
So we did want to, again, there's a quiz. Excuse me, those of you online, you'll get an email reminding you to go to Canvas, fill out the quiz. But we wanted to take a few minutes, ask some questions and answers, ask some questions, and hopefully we'll come up with answers to those. But that being said, we thought that just sharing that collaborative decision-making process was very valuable because that can be used regardless of whether you're evaluating structural systems. It was used very simply on evaluating the foundation system, but you can take that to any type of decision on a project, whether it's selecting just the exterior skin, whether it's selecting a particular layout of materials, whether it's selecting air conditioning system, electrical requirements, anything you want. But it's a great tool to actually be able to take something that could either one become just very cost driven, or I say decision by bully. Basically, the loud person in the room gets to make the decision, or what really are all the different factors that weigh into a decision. And you can take this to a business case scenario. You know, if you're doing a building expansion, what are the benefits and drawbacks of that? If you're going to spin off a company, what are the benefits and drawbacks of that? It's a way to take a very complex decision and take a lot of subjective material, make it into an objective process, and really clarify what you end up making the decision. And it's also documented. It's easily defensible in the end result. Do we have any questions for those online? We've got a few extra minutes. We are running a little bit early, which is great. You can always have additional time. But I don't see any hands raised. You're all very silent, or you're just talking without turning your microphone on.
I have no questions. Thank you.
All right. Thank you, Christy. So again, thank you all very much. We are excited to have some visitors actually here. Appreciate it. But again, I think this was a great session. And again, it shows how 3 different projects within all of like a block and a half can be radically different We've got radically different structural systems. We've got radically different foundation systems that we covered in a previous session. So when you go home for Thanksgiving, you can pull these up, show your parents what you're learning at school, and it's a good thing. This is the real world here. So with that, if there's no other questions, no other comments, have a wonderful Thanksgiving. Have a safe Thanksgiving. All right, thank you all.